students, welcome back. Now coming to the next topic in the subject compiler design was DAG representation. So what is this DAG? The DAG stands for directed acyclic graph. So it is a graph which is a directed acyclic. Syntax tree and DAG both are graphical representation. So you already know the syntax tree, means the generation of the paths tree. So how you are going to generate? Suppose if a plus b is there, then plus a and b. So like this you are going to construct the paths tree, that is a syntax tree. So here what is the main difference between the DAG and the syntax tree? The syntax tree and the DAG both are graphically representation. And the syntax tree does not find the common sub-expressions, whereas DAG can find the common sub-expressions. So the main difference between the DAG and syntax is syntax does not find the common sub-expressions. So whatever the common sub-expressions that are present in the given grammar, so the syntax cannot able to find out that. Whereas DAG can find that and make the tree reduced, means the size of the tree can be reduced by finding the common sub-expressions. But the syntax tree cannot find the common sub-expressions. So if you see the examples, you can get the idea what is this common sub-expressions was. Okay, so later we will discuss the example. First, let me explain what is a DAG, what is a directed acyclic graph, and what is the algorithm of this DAG. And another usage of DAG is the application of optimization technique in the basic block. So the DAG is finding the common sub-expression. At the same time, it has a technique of optimizing technique in the basic block. So finding the common sub-expression is one thing, and you have to optimize that tree. That graph you need to optimize that. So it has another usage of DAG. Is the application of optimizing technique in the basic block. Okay, so in the basic block, if it is having the common sub expressions, then it will find the common sub expressions and it is going to optimize that common sub expression. To apply optimization technique on the basic block, DAG is constructed tree address code, which is the output of the intermediate code generation. Okay, so syntax tree is a tree, and whereas a DAG is a graph, means you can get the closed loop also. So the DAG may consisting of may occur the closed loop also. That is another difference. It is a tree and it is a graph, and it has the DAG is going to construct the tree address code, which is the output of an intermediate code generator. Whatever the output that we are getting from the intermediate code generation, that is in the form of tree address code. So if you want to apply the optimization technique on the basic block, the DAG is going to construct the tree address code. So first it is going to construct the tree address code, which is the output of an intermediate code generation. Now let's see the algorithm for the construction of the direct acyclic graph. So what are the input you need to take and what is the output, and what are the steps that you have to consider by taking the inputs to reach the output. Input, it contains a basic block. So I said the DAG will take the basic block to optimize the expression. Output, it contains the following information. The output may contains, each node contains a label. For leaves, the label is an identifier. So whatever the nodes that it consisting of, those nodes has labels. Okay, like A, plus, minus, or B, ID. So like that. So whatever the leaves here you can see, these leaves are identifiers. ID1, ID2, ID3, ID4. So the leaves are always identifiers. Each node contains a list of attached identifiers to hold the computed values. So whatever the nodes that are created here, these nodes contains a list of attached identifiers. Not only the single identifier, you can attach the list of identifiers also in the DAG. Now let's see three cases will be there. I have written three cases. The case one is x is equal to y operator z. So the operator may be anything, the plus, minus, divided into, and whatever it may be. And case 2 is x is equal to operate y, and case 3 is x is equal to y. So first I want to explain these cases, means I want to represent these cases in the algorithm. Later I'll explain the example. So now let's see the method. Step 1. The step 1 is, if y operand is an undefined, then create a node. So what's the equations here are given? In the case 1, x is equal to y operator z. Okay, so this is an equation. So according to the algorithm, what I have to do? If y operand is undefined, so this y and z are the operands. These are the operands, nothing but the identifiers. And this is an operator. OP is an operator. Suppose this y is undefined. Up to now you are not defined. Then what? It creates a node y. Suppose if z is operand, is undefined, then create case 1, create node z. So just create operator. Okay. So node y you have to create and node z you have to be created. Okay. And whatever the expression that is assigned, that is an x. Okay. Case 2. For case 1, that is x is equal to y operator z. So in the case 1, created an operator OP whose right child is node 2 and whose right child, this is the right child, is the node 2 and the left child is the node y. So node z. Okay, so no, not 2, it is a z. So you have to create an operator. This is the operator whose right child is z and the left child is a y. So that I created. In case 2, check whether there is a node operator with one child node y. So you need to check. So what is in the case 2? The case 2 is equal to x is equal to operator y. Okay. So that is the question. X is equal to operator y. So here in the case 2, check whether there is an operator, node operator. Here it is node operator is there with one child node y. Is one child node y is there? Yes, it is there. Now case 3, that is x is equal to y. Node n will be node y, and this node n, whatever it will be, it's a node y. So these are the steps you have to follow. So whatever the cases that you are given, so just represent it in the graph model. And you need to take care, here the left operand will be assigned as a left child and the right operand is assigned with the right child. Okay. So the output for the node x, delete x from the list of identifiers and append x to the attached identifier list for the node n found in the step 2. Finally, set node x to n. So this is the thing, you just assign x to n. Okay. So if you see the example, then you will get a clear idea. So in the next video, I will explain the DAG examples, directed acyclic graph. Thank you.